share with other people and have this captured.
One word.
Yeah. Yeah. Cool. So I think we're at a pretty cool place with SimPEG right now. It seems like people are starting to know that it exists and starting to use it without our knowledge, which is pretty cool. I got an email even yesterday from Jared at the USGS, and he's saying that all the new interns that he's bringing in, he's training them on SimPEG.
Oh, really?
Yeah, which is extremely exciting. So yeah, we're in a pretty cool place.
Okay.
So
Jared is
USGS.
Yeah.
Jared,
yeah, and Yago is also doing that, right?
Yeah, he's the ones that are coming in, and Andrei Swedinsky is also trying to get his students on.
Yeah,
as far
I
as
was helping one of his students. Like he's interested in like he's like a tiny man.
Oh yeah, yes.
Actually, had a chat with him this week. So,
Yeah, so it's pretty exciting. I think like we're in a place to, go from just our group and our connection stack to have this being the go-to package. Yeah, and so I wanted to try and use today to like touch base with our core team, which is in the room today, and go from there to figure out like first of all, like make sure we're up to speed on new changes, identify some priorities, and go from there. So I know we started like sketching out this issue, but I was wondering if it'd be worth like a quick go around in the room, just like what are people's main priorities for the day? If you get one or two things out of today, what do you want them to achieve? Yeah, and we can perhaps go from there. Yeah. Cool. Who wants to start?
Yeah. Like I didn't have specific point here I put in the issue or like reporting what we had in meetings, but I think my idea, I think it's more the high level idea saying that today we need to discuss about like as you mentioned that several months ago, like SimPEG 1.0. What do we need to have a SimPEG 1.0 release and try to have a bullet point list and assignment for that both fit like what the community needs, but also our interests. So I think that will be a major output from that meeting.
Clockwise, counterclockwise.
Oh yeah, I was just waiting for him to do that.
Yeah.
Or random. That's the other way.
I'll go. Me, it's simulation for potential fields. So bring potential fields to your standard of EM. And then I think another big one is that we were talking about it, but it's the survey / receiver class, so that we avoid duplication of locations. So how do we index? How to be able to query a survey for unique receivers, which I think we'll have to rethink the way we're storing, or we're like saying a receiver is oriented in what direction on that. So I think we should brainstorm about how to do this.
So what I'd like to get at today is just kind of identifying the areas that we can focus on to kind of push the speed forward a little bit more, like optimize efficiency. I'm going through things and just kind of identifying places that we need to improve the code that's in SimPEG and improve other code that SimPEG uses outside that also that we could contribute to, like
As solvers.
Yeah, solvers, sparse matrix. If there's any way we can help SciPy with sparse matrix libraries to maybe come up with some sort, because they don't have like the compressed sparse column times compressed sparse row optimization, like that function, like it always converts it from one to the other, and then does the multiplication. Just things like I said, identifying where we need to focus on code in SimPEG and where we could add to the other stuff outside.
Yeah, so from.
General manager.
Kind of follows that. So I'm not a programmer, right? But I really would like to use this as kind of consolidate. Okay, exactly. What the modifications to the framework have been, and really kind of comes back to okay, what is SimPEG 1.0? What do we need to do to get there? And then Joe is coming on board in the beginning of January. So I'd like to have some kind of an overview path of okay, generally, what directions are you going to go in? How can I facilitate that? And there is also the potential for another postdoc to be added on here. And so kind of having that broad scale overview, where the holes are, what we need to do to really accelerate the growth, and in particular to develop the EM, mostly that needed to learn to the highest priority at this point. Kind of have a global concept of that. I think that would be good.
Yeah. Just some go through. Thanks, that would be an important step. At least to me, is in handling large scale EM problem. So I think if you kind of other than there are multiple, really kind of problem. It is actually problem dependent, but if you can pick one, kind of, and then establish what are the important items that we need to accomplish, and kind of have a little bit of agenda who's going to do what. That'll be great, because one day is not really enough to develop something, but can have a plan. That'll be good.
Is that mostly captured?
So you do later.
I mean, I think this captures from my perspective the main things. I think, yeah, getting the idea of a SimPEG 1.0 release, sketching out what that is. I think too, giving a bit of thought to broader communication strategies and things like that, with respect to our website, the docs, all that sort of stuff, because it's starting to become we have. And maybe this is worth a brief conversation over lunch or something like that. The Google forum, we have Slack, we have Scuf. We have a lot of different communication channels. And right now, I think we should get rid of the steps. We're not maintaining it, and so we should just
Even the Google group.
even the Google group is not great, but Slack doesn't necessarily scale. So it might be worth chatting about, I know the Jupyter team is using Discord, so we can check some of those things out, or even just creating a GitHub repo and people can just create issues and something like that. So I think a brief discussion on how do we actually want people to be interacting with us.
Yeah, maybe add the translation.
Yeah, that's
Around that time.
not website. I think that's actually something that we could improve the Pangeo website. Cool. Okay. I think this perhaps then gives us a bit of an outline for the day. I think that these are all sort of related to this simulation class.
Yes.
This is a subset. I think it's a distinct enough topic that we can dive into that independently. And then this, I think, perhaps follows from talking about the simulation class. Is figuring out first from the structure and then going to that makes sense.
Yeah.
Okay. So what I was thinking is that it might be worth just sketching out what the SimPEG framework currently is, or what the simulation class would do to it, and then just so that we're all sort of on the same page and can start from there. Saki, would you mind pulling up the SimPEG website and just so we have the current framework to compare with. And so would you mind just sort of like fixing the camera so that you can see some of the board? Yeah, so oh, you can put it back. Okay, so that's what we pitched in the paper, what SimPEG is. There's some interesting things that are there and that are not there. There's some things that are missing, which I think is actually important. So first of all, the simulation refactor, the biggest thing that it's targeting is this pair, right? Is get rid of the survey and problem distinction. So really getting rid of the problem class. The other thing that I think is missing that should be on this diagram is data. We don't actually have data explicitly stated as where that comes in. And before that was because it was implicitly in the survey. Yeah, so I think that's the place to start. And so the thing that I've sketched out is like roughly what the new simulation class looks like. And I'm just drawing this because that was like my sketch. So in this case, the way that I see things a bit being structured here is we've got data. And in this case, survey actually, so the survey basically has just like sources and receivers and their locations, and maybe some useful utilities like the ability to sort by frequency and stuff like that for the frequency domain. But other than that, it doesn't know anything else. It previously used to know about the data and the uncertainties, and so it no longer knows that. The data knows what the data is, and takes a survey because it needs to know about its geometry. Okay, and then we also have a simulation. Oh, okay. Move the camera over to
Yeah. Let's say easier into that.
better.
Yeah. Yes.
Okay. Sorry.
Hold on. Don't move.
Okay, so we have the simulation, and the simulation now takes a mesh. We also have then a. I'm just going to move the guys because I think this. Okay, so we have the survey, and now we have a simulation. Also takes a survey. Is making sense? And then these guys, so currently the way the simulation class is working, and this is something I think we should discuss, but those two are combined in groups. Often. And let's see.
The optimization.
Yeah, the optimization comes into the, so I get to Yeah, the optimization currently comes. And then we also have so what's different between this and that? So the survey class is probably one of the biggest differences. Is it's very much more lightweight. All it knows is geometry. The data class now takes priority in the simulation. So then these guys are basically functioning the same, although the data misfit is now different. So the data misfit used to only just take a survey because the survey knew about the data and the survey was paired to the problem, so it also knew how to simulate it. Now, the data misfit needs to take data and it needs to take simulation. Regularization hasn't changed, and then once we get to this level, nothing's in the code, this means that, for example, the depred method was on the survey, it's now on the simulation. And ideally, so what the base simulation should have, and I think this is something to think about too, is I think that we actually want a base SimPEG simulation, and then we want a base simulation, and then perhaps like a base simulation that has sort of a discretized mesh and all that sort of stuff. The distinction being that we want to incorporate something like GeoSci.xyz. He doesn't need a SimPEG mesh, so like we don't want to load down that object. So the basic thing that a simulation needs to be valid, I would see basically it should only need 3 things. So it needs a depred, it needs a JVec, and a JCVec. And with that, we should be able to invert it from the simulation. So as long as it has those things, then we should be able to work it. And so
Right now you have a mesh, right?
yeah, but it doesn't have to be instant. So right now, the way that the simulation class is written is none of those things are actually required. But it might be nice for transparency to actually have an even later weight class that you inherit. That like this is the bare bones of what you need.
Something that says like, oh, you must instantiate these 3 methods. Like if not, it's not going to work.
Yeah.
Or it's not implemented.
Yeah, exactly. So the base class, like I think actually should just be used with not implemented errors.
Yeah.
And then you can inherit that thing and go from there. Anybody have questions about sort of this diagram? Does this kind of make sense?
So the whole goal was to be able to so where's the heavy part? It's just only the data.
Yeah, the data could be heavy. And then yeah, the mesh potentially, but it shouldn't. I mean, the storage of the meshes is reasonably efficient. Yeah. So it was like sort of twofold: is the ability to serialize, which you can do before, and then the just clarification of the framework. Because I think explaining the problem to people is just like so confusing for the
It's still not easy, but
yeah, but it's a little easier to think about a simulation.
yeah.
And then like if this is actually all that it means, then that's a bit easier.
Just to go one level down, your source and receiver class at the end is survey or is it
So it ends up going to both. So the survey, the data class actually has a survey property.
Yeah.
So when you instantiate a data class, you provide it observed data and you provide it.
So but so basically you do like data.survey.receivers.
Yeah. So then this then means once stuff is plugged in, we can start to serialize.
So what can we serialize like a little bit smartly? Like let's say, although that's an input, I don't want to store something. Like I don't want to actually like serial. I don't want to even put it in your serialization. Like, can I let's say I have an RX location, for instance. Somehow, I don't want to actually store that. Like when I'm making a JSON, I don't want to like output it. Is that kind of easy?
Well, you can do your own.
Okay.
So you can write your own serializer. The basic approach, so the basic purpose of the serialization is that everything that you need to recreate the class as is serialized. But nothing more than that. So there should be absolutely no duplication of information when you serialize. So for example, if you talk about dipole receivers, we should only serialize the A and B electrode locations. There should be nothing like unmuted point or something like that that gets tossed in the serialization. It should be exactly like a unique description of that object with no duplicate information. So, does that make sense?
Yeah. But there's a little bit of detail. So in the same case, if you think about that, there's a unique electrodes, for instance, right? So let's say you got basically like 500 unique electrodes. There are a whole bunch of dipole combinations. Let's say about 100,000 dipole combinations. So in that case, I don't want to store 100,000 dipole combinations. I'd rather store like 1,000 electrodes and maybe just like a data indices for each of them.
So that comes to this, is that I agree. We need to be thinking about the survey class and actually how we store sources and receivers, and do a better job of that, because I don't think our current approach scales.
Right. So so that we can that's problem dependency you write some sort of serializer for yourself. Is that?
I think what we should do, we can jump into this now if that works, but I think we actually need to rethink how sources and receivers are stored. So, because right now, all right, before we move into this, are there any other questions or things we want to discuss about the changes in the framework?
Well, we mentioned yesterday the question about inverse probability learning things correctly or also moving that, but I don't know if that's a high priority, but that was that it's mentioned.
And also, can you it's an EM specific, but can you comment on how fields sort of moves there? It's always a little bit complicated because it actually you once you enter the fields, then it's actually not available in a simulation class. It's more in an inverse problem. You know what I mean? Once you store that field, it's not in the simulation class. It's more like a separate entity. It actually moves around in
It does, right.
So it's actually basically in a.
Okay, so the way that currently works, I'll give a quick overview, and then this is something that I think we should absolutely think about, but might not be one that we go deep into today. So the simulation, you're right, Sagi, is when we're computing the data misfit, for example, we store the fields because when you're computing JVec and JTVec, you don't want to be recomputing the fields. So when the data misfit asks for the output simulation, it asks for fields and it asks for JVec. And then we pass the fields around in the computation of JVec and JVec. I don't think so.
Just because it lives in memory and then just pass it around.
Yeah.
It's a pointer.
Yeah.
But it's not stored. It's not stored by a simulation object.
No. All right. So none of that. I guess nothing has changed with respect to that.
Okay.
I agree. It's something that we could think through, but I haven't spent time.
No. I my question was it's exactly the same as before.
So your projection matrices then to go from fields to data, where do they go in that?
So that's the heart of the question that we have with the way that sources and receivers are stored right now. So right now, the projection matrices are stored by each individual receiver. So each receiver knows about how to interact with the mesh to get its data, or interact with the fields object and with the mesh to get its data. So if we want EX real in a frequency domain experiment, the receiver needs to know that it's grabbing the electric field. It's grabbing the x component, which is the top part of the vector, and then it needs to look at the edge x grid to build its interpolation. So the receiver keeps track of all of that.
So the projection matrix is stored in a receiver class. Each receiver class has a projection matrix.
Yeah.
Which could potentially very inefficient, depending upon the case. Yeah. So yeah, it's worthwhile to talk
Yeah.
later.
So to come to Thibaut's point real quick, and then let's maybe jump to the survey, because I think that's where all of these conversations are going. Right now, I think this distinction isn't really necessary. I don't think that we necessarily need to create an in prob.
Yeah, I was looking at the class and
It's like, it's a silly class. I mean, it made sense at the time, like to make a statement of the inverse problem. But I think that what this should do is we should basically, I'm going to rewrite this here, is that we should basically just do data misfit plus. And then the optimization. And then
potentially inversion is doing right now is run as store directives and run.
well, so so right now these are both pretty lightweight classes. This what's a little subtle, and I think that this starts to become a touch more problematic when you want to think about doing joint conversions, and potentially be shifting relative weights on like having more than one data. Right now, simply cannot support more than one. The idea of more than one change, like parameter that's changed. Right, it's the way that the beta directive is written is very much assuming that you have a single data misfit.
Yeah, I will remove all of that. I'm pretty sure.
Yeah, and so the objective function class is built with the idea in mind that like you can swap out the multipliers on the objective, on each piece of the objective function. So if instead of having just a data misfit and a regularization, we have phi1 plus potentially each of these, you could have a directive that goes in.
So that's basically what I did. Is like I have actually like several derivatives. I want to do so, but okay, I have to go fairly deep. But that's maybe I can share that and show what I did at some point.
That would be great. Yeah. Yeah. So that's basically like erasing this and just extending those arrows is the idea. Yeah. Yeah. So I think, and actually that's a good point. Would somebody mind starting like a SimPEG 1.0 or even just commenting on the current issue that we have? I think that like this, and you can take pictures if you want and just toss them in there, that this refactor would be an important piece of that, is like making sure that the framework is right when we say this is SimPEG 1.0. I think we want, I guess, both the simulation and the inverse problem in place. Right. So we're going to move on to sources and receivers. Any other questions?
So if you change these classes around and change the boxes, what's sort of the downstream effect of that? I mean, is this pretty complicated, or do you have to zillions of places that things have to be changed?
The simulation one is like a little deep in the code because it does touch everything, or it touches all of the different physics. What's nice about this refactor is it actually just touches like just the inversion piece, because that's really nicely decoupled from the forward simulation. So this is actually a much more tractable, easy change than this.
And what again was the distinction between the inverse problem and the inversion?
So the inverse problem, the like conceptual idea of the inverse problem is basically this thing is a statement of an optimization problem. So here, this is where you say minimize whatever with respect to, and then
It's like
you have like
it's before you act. Like
yeah, before you act. So this sets up the map, and then this basically is just like the orchestrator. So it actually then says, okay, now you've given me an inverse, like a mathematical statement of an inverse problem, some sort of optimization routine that is fitting for that. So if you have boundary constraints or whatever, you need an appropriate optimization. The inversion then says, okay, I also have these directives that potentially cool beta or estimate the first beta or are basically all of the instructions, the orchestrators of how this thing is solved. That's what the inversion.
Do you need part of that inverse problem definition to kind of be tied into your regularization function? Because or where you have regularization, because if you're in your inverse problem, here's where you say like, oh, I want to minimize, the log of something or some nonlinear function of something. Right? But then you've already specified the regularization beforehand?
Yeah. So you specify, so like basically at this point, we have a phi d, and we know what that is, so it's maybe an L2 norm. And then we've specified a phi n. And this can be L2 or L1 or whatever you want. And then the inverse problem is then actually when these things are first assembled.
So I should get linear time, right? It's doing it's calling for the Hessians of each, and for the gradient of each, and it's summing them. That's what the inverse problem is. That's all it's doing.
Okay.
It's calling the misfit and say, give me your first derivative and your second derivative. Add them.
It assumes like your model is defined that way. So it's already like that's the assumption. Like,
Okay.
So like
I thought that's kind of where you were.
right, like it's actually missing there. So like but this workflow is assuming like we have a definition of your model. So but we do have like a mapping, for instance, which is not sure that's actually worthwhile to put that in there, but that's what we're doing.
So the mapping come into the simulation side of it.
Yeah, the mapping is still coming to the simulation. So
All of them. Regularization is its own natural misfit.
yeah. Actually, I don't know if this one
Misfit is
does
you should.
we could
Be fully symmetric.
fully mappable. But does that answer your question then?
Yeah.
Optimization holds the current state of the model. So model current optimization knows about it.
Cool. Okay. So you get a picture of that? Is that okay if I erase? You can use yours too if you want, because then you can dump it on your.
Just like very.
Yeah, so the status of the simulation is basically it's through most of the code base at this point. The other thing that I've been doing has been refactoring, is renaming all the modules. We can dive into that later today if you're interested in seeing that, or we can, we can maybe do a quick overview. But trying to use like a style module names and all that stuff. So it's basically through, I think, almost everything except potential fields, and it's not in the examples yet.
Is that everything?
Yeah, I think so.
Whatever is inside.
Yeah, I mean, it's straight raised monolith. It's pretty lightweight. Yeah. So yeah, so we need to work on potential fields, but maybe we can spend some time deciding.
We need to know how to do this.
Yeah. Okay.
Because we're implementing the things that we did, we need to know how we're going to structure it. Before we do the exception, let's do the norm.
Yeah.
Wow, so it's such a nice whiteboard. It doesn't need any Any blue?
It's really nice.
Brand new.
And then did somebody get just the inversion rethinking in the issue? Or like SimPEG 1.0, etc.
Why those in the motion? Joe, how, what's your plan about it? What's the plan to store tree meshes instead of less tree meshes? Because those are that. You said it's not too heavy, but actually they can get pretty heavy, right? You need to store all the levels and the neighbors and all that stuff. Like what's
So the idea, what happens right now, like it's serialized, so it can be pickled. It's serialized pickle right now.
okay?
Um,
That's compressed.
basically, it creates a list of all of the levels of every cell, all of the locations-ish, like index locations in each cell, as well as the initial H vectors and origin of the mesh, and then it just recreates every time. Like it just stores that part of it and then recreates the entire mesh from that column.
Oh, that's
That's
great.
Yeah, I don't feel like it was too heavy. Like, it's kind of uses the same like insert points method, which happens pretty quickly. Right? It doesn't have to call anything.
Can't wait for on the first creation. That's good.
And that's just, I mean, you're just concerned about sending it between. What is your use for serializing? How do you want to do that serializing?
Well, ideally is to store whatever experiment that you have done, right? Where you don't want to have to rerun the script, you just like deploy it either on the remote machine or for yourself. That's fine. That's it. I don't know yet.
I mean, it pickling it should work. Test stuff that works. And that's,
Okay, so sources and receivers in the survey class. So the way, just to make sure everyone's up to speed on this, the way that the survey currently works is that so the survey has a source list, and each source has a receiver list. So and then each source has its own receiver. So
each receiver with some of those.
yeah, each receiver has its own looks. So this is that's a really good point. Because that's a bit confusing. So these guys have locations. Essentially, MT doesn't need locations, but also have locations. They have frequency, they have potentially like an orientation. These guys also have an orientation.
Yes.
And it's essentially a component. And so the way that that's used right now is like real image. Or if you're doing something like KMI, well, no, that would get
Ooh, you're kind of going off that thing, so yeah.
yeah. So, and then each receiver also stores its own projection. So it knows how to get stuff from the grids to yeah, and so if receivers are duplicated, that's okay. It's still it's the exact receiver is duplicated. We're not duplicating projection matrices. So if I provide RX1 to source 1, then I'm not duplicating. But where the problem is right now, if RX1 is EX real and RX2 is EX image, I am duplicating because each of those is which is unfortunate because it actually does end up significantly slowing stuff down. And I'm sure with DC we end up dipoles making a bit of a mess there too. Why we originally did this is because it's when you are solving the forward problems, you are looping over for each source, and then within that just for each receiver. So it's just a loop, like nested loop. So this is very much how the code operates. So it's natural to think about it that way, but it's not necessarily natural to store it. So
And also,
yeah,
you could have same locations, different orientations, but they will be considered as different receivers. Even though they have the same place, they should use the same projection matrix, right? Other than maybe the components, but through the phase.
yeah.
That kind of depends, like, because so it's like in EM case, each component lives in a different place. So it's actually like, let's say, live in a face, live in edges. So like your projection matrix is actually different, like for each component, like each orientation, for instance. So like it kind of depends.
Yeah. So this is, first of all, this is this current setup. Are we clear on that? One subtlety that is confusing when you explain this to people or make sense in the code is that a receiver can have multiple locations. So like when you say receiver, you think of like a measurement device that measures things. But when we say receiver right now, it actually means like something that is looking at EX, and that something could actually have locations. So this essence. So what I think we should think about, and this is something I haven't spent tons of time on, so it's very much a sketch, and like that's why we want to try to do it here, is to actually start thinking about the survey. So it's sources and receivers sitting on the survey and being basically treated at the same level, and sort of thinking of it as a data frame. And so thinking about it as basically if we have sources along this axis. And we have receivers. And it's potentially multidimensional. And by that, what I mean is that if we have real and imaginary, I would actually extend that dimension this way, so that then we can have, you assume then that like if we're going in and out of the page, we're along the same location. So you store your projection. And so with this, if we can think of it like a sparse matrix. So for example, if receiver 2 was not listening to source 1, like we could have basically like an indicator matrix that just says who's listening to what. And then this would be the thing that we move over, so that you can basically condense and grab only the receivers that we care about. And then with this, each projection matrix could then be stored like at so this receiver should have its own projection matrix, and it can then just be applied across all pieces. And then if potentially there's an RX at the same locations but really match, then we know that we should be looking at the same projection.
That's great. The potential field, that means we only have one column because it's single source. So we could have multiple components through the board, right? So when I calculate the matrix, the dense matrix, it's a single call for all of the implications, and then through the board for all the components.
Yeah.
One thing I can maybe think right now is a smart matrix, and you might need to be smart about how we order the source and the receiver, so we get like not like random 0 and 1 everywhere, but like will be organized. I don't know if that makes a difference.
I don't think that should matter too much. Yeah, I mean, it's a survey start getting absolutely enormous, maybe. But
And at that point, also like trying to minimize, you're getting down to cache level type of things. The processor trying to minimize your cache misses.
well, and that's something where like I think my intuition here is that X-ray is a good approach for this. Is because X-ray lets you like think about it's set up for indexing multi-dimensional data arrays. So it's like pandas, but for actually n-dimensional. And they thought a lot about how to store things. So what's nice about that is with our current data class, like it's helpful to be able to index into the data by source and just say, this source and this receiver, give me the correct data, or I want to set data. You can do that with XORA file natively, because you can have named and labeled access. So each source can have its own unique identifier, which it already does. And then those can be the access for like the XORA.
Yeah. So the XORA just holds all the sources and all the receiver objects.
And they've thought about going large scale and how to save stuff and trunk stuff. And so if we get there, they've already thought about it.
Just a thought like that, but more asking them more. It's like I'm just thinking of the way we're thinking for the code and drip for the sources and receiver with moment. Yeah, like basically going by indices. That's we get like way closer to that. So.
Yeah, so like a kind of related, I like how, abstract, but I love like how survey and receiver is structured in SimPEG. But numerically, it's not actually as clear as how UBC code is written. So if you think like a UBC code, like what it does, like it has all the sources and all the receivers, and then basically like it generates a big one projection matrix. And then once you project like all the possible location, then they have a mapping function. Just like okay, some of them are not used. So it's actually like numerically kind of in an algebraic sense, it's easier and actually faster because it's one matrix vector multiplication. So yeah, I'm not sure what's somewhere in between. It's so I think what I don't like about current approach is actually we're storing each projection matrix in the receiver class. So like for instance, in the airborne case, for instance, like let's say you got 1,000 sources, and then you may like you're actually storing like 1,000 projection matrices in this case.
There's one giant.
Right, rather than one P matrix, because like in a spatial location, what you need is just like a sparse matrix having 1,000 location. Right? So yeah, so it kind of it's a trade-off, but if you can so I mean that's a question then like do we really need to store the projection matrix in the receiver class, or like we could potentially just store it in a simulation class, or like somewhere I don't know, or survey class or something like that. I'm not sure, but so I think somewhat hybrid could work well because it's nice to have those structures, right? But we don't really necessarily need to like store the projection matrix there.
Yeah, I wouldn't put it on the simulation, but we could do it on the survey. And I think like what this is suggesting is a bit more of a flexible framework. Because what would be nice to be able to do is to basically be able to subclass the survey class, so that if you have these custom cases where like you know how to efficiently build,
yeah.
then like you can just do that. So as long as we get like the base structure right is what's
right.
I think we want to enable. So I think there's maybe a couple use cases to think about, and like what should the methods be? Because one thing that like right now in the code we have to call some things from the sources, and then we're calling some stuff specifically from the receivers. But you could actually, and this might be a better way to go. So right now when we're asking for the projection matrix, as you point out, we're asking the receivers, we ask the receivers to keep their data. What might be better is to ask the survey.
Yeah, because then like you don't necessarily need to loop over all the sources and all the receivers, which could be like a very inefficient.
Yeah.
Could be like depends upon the case, but especially you got lots of sources and lots of receivers.
How do you extract? You just do a call on a sparse matrix and ask me for that row.
Right. Like that sparse matrix. It's like I said, you got two sort of set, like one big sparse matrix that have every location, and you got another mapping function. It's basically a diagonal matrix that whether 1, 1, 0, 1, 0 or something like you're just like discarding all the unnecessary location later.
That gets like right on the road.
Potentially.
No, that makes sense.
So one of the things, if we're thinking about a survey class like this, maybe let's write out like what are actually its properties and its methods. Is that helpful? So we have, because the other case when you were mentioning, or when we were talking about the survey computing data, I think that'll simplify the integration between MT and the frequency domain EM code. Because right now with MT, you need to compute and store two polarizations. And like the frequency domain EM code conceptually only lets you store one field per source, or like each source, there's only one thing happening with it, whereas MT you need both polarizations. So each source actually has two different source terms attached to it. So this might let us abstract. So if we have, okay, so we've got the survey. So now in this case, it has a source. It still has a source list. We still need to know which source it is. We still have a receiver. Well, now I think what this is suggesting is that the receiver list is no longer inside the source.
Yeah.
Receiver list.
Component list and orientation list.
Okay, so that's a question. Is where do each of those like
Yeah. Is that going to be like a sort access like that? So you have receiver list and then you access the orientation, or you
Yes,
want
for EM, your receiver is oriented, right? So there's your component list. And so then you just index this data is this source, this receiver, and this component.
so then I think what that means is that the receiver still needs to keep track of its own
Orientation.
or its own orientation.
That's fine.
Okay, so we have each receiver has a orientation. It has locations. And then it potentially has this, maybe like, I don't like this word, but it potentially has. And this, by this, I mean like the idea of real and imaginary.
I would put component outside, but
Well, this could be a component list.
I know, but we're talking about a third dimension, right? So you kind of want to, if you're going to index the third dimension.
Yeah, or like even in, as you said, like multi-dimensional, but then you have like component, but you can also have like a fourth axis, which is the orientation. So it's a matter of like, in that case, are we bringing them all at the same level here?
So what I would see, and I think this might help tease this apart, is that we need to be able to loop. So we loop over sources. That's great. And then for each source that we're going down, when we hit this receiver here, I need to be able to go into the page and then start getting all the things that I need to compute just on this receiver. So this receiver needs to know what its location. It needs to know what its orientation. And then potentially the extra dimension. So this can have sort of multiple properties attached to it. But then this outside the page is then potentially the real impact. So it has.
It's detached, right? It's not attached to the receiver.
Still has to be attached to the receiver. Because we're asking, so it's a question of like who owns which dimension.
Is it really like, I feel like that kind of is the same sort of thing as an orientation. Feels like the same thing. X, Y, Z, real imaginary. X, Y, imaginary, or X imaginary, Y imaginary. They're all just different components of this one long vector of things, right? It's thinking about like a vector as kind of as like a spatial thing. It doesn't have to be, right? A list of things.
Yeah.
The tricky thing with that though is, at least with the EM codes, and maybe this is like a challenge with language here, but the orientation, if we're just doing X, Y, Z, those are different grids and are each going to be a different interpretation. And so it's a question of like which way.
Let's go let the receiver apply, because eventually you're never going to do X, Y, Z. It's going to be like an inline. It's going to be a loop, whether the loop in space, right? your receiver is your receiver, is going to project the field whatever it wants. It doesn't have to be Cartesian, it's your RF style. It's fine if the receiver knows its orientation, sure, I mean, you can define that. But
I guess
So then, at that point, then, like, kind of thinking, are your components just restricted to being either real or imaginary? Like, in the case where you have all three things, if you're looking for all three spatial vector components at one location, do those then become components and they're not part of the receiver orientation, right? So, yeah, like, the orientation is part of what the receiver is itself.
so. Right now,
You have X receiver, Y receiver.
yeah. So right now we have that. We have like if you want an X receiver and a Y receiver, they are independent objects. Which at least for the EM piece, it works well within the code base. Because each of those is grabbing a different like grid, a different chunk of the vector. And so conceptually it's much easier to work with them as independent objects. So, okay, I guess the way that I am trying to think about, well, maybe that's a fair, so, okay, so the way that I'm trying to think about receivers, and this, I think, well, is like a set of things that have the same location. And then,
Set of things in the same.
yeah.
But like, what's the? I'm a little bit lost. Like, what's the kind of question here? What's that? What are we really?
how do we duplicate less things, right? How do we store things that are, if they're all the same, they'll come to the same place, don't have to, we can just call, give me all the receiver locations, you get all the unique receiver locations, no duplication.
Oh, okay.
But then we still need within the code base to know like which receiver is grabbing from which grid, right? So EX versus EY.
Yeah, like a. Like how I was thinking, I kind of want to keep the current, like I don't want to change the current structure like that, but like have a separate, index or like just an index file. So once you you generate the like a current style, you have a source and receiver, and then loop over generate whatever source list. Then you pass that to a survey, and survey can figure out what is unique and have index file.
It's a really hard thing to do because at that point, what you're trying to do is point by point compare NumPy arrays of growth. And so that's actually a really expensive and potentially error-prone computation. And so that's something I think we want to shy away from.
Okay.
And so what I was hoping was sort of the idea of thinking about survey as like a sparse matrix is like we can then get away from that. But like we don't have to do any post-processing on the thing that you've given me. There might be a utility where you can set up the survey like the exact same way as you have in the past. But like the thing that is actually stored, we don't want to be going through and looping over and comparing.
Okay. So for instance, you want to put a unique location and then indices like receiver ID and source ID. Basically, use this style.
I think they solved the problem for us, and you just need to emulate what they do. Okay, let's take inclusion exercise. That's because this is going to be like the most useful case, right? You get a spreadsheet of data. So you X, Y, Z, data 1, 2, 3, 4, 5, 6, 7. How are you gonna digest this into something? Let's try to do it.
Let's take specific.
Because we can we can think about it multiple ways, but at the end of the day, that's what we want to do, right? We want to bring data from the outside and then run with it.
Yeah. I'm just trying to think, is there a specific application we want to think through with that?
TEM, FEM, it's all gonna be the same.
Okay.
I think so.
Let's think through airborne timing.
Sure.
Start there, and then we will break it down. Okay, so if we have so if we have airborne time domain, so we have a source, and each source, well, each location, then there is a coincident receiver location, and then this pair is between them, and then we have the times. So each datum has a single source, or like each is the thing that we want to think about.
Let's do a block, one source and multiple data attachments. So it could be one source, one receiver, whatever.
Okay, so we have
Usually contractor gives you for an R1, so it's going to be X, Y, Z, and then time 1, 2, 3, 5, you need to digest this and bring it up.
sure. So then let's do 3 components, X, Y, Z, and then each of those then has a time series.
And the contractor will give you some geometry about what's the loop size and what's the
Yeah, sure. So okay, and then this has size, maybe a waveform. Whatever. So
orientation. It's a orientation from
okay, and then if we're so yeah, I mean this one maybe is not the because the current structure works really well for this. This like fits. This is the first one that's here because the like each source actually has a single receiver.
Yeah, so maybe put something on the ground.
Yeah.
Maybe like a cycle survey.
I think let's hold off on that because I think that keeping track of that goes is slightly more.
Pull.
Excellent. Okay, so we have okay, we're doing grounded time dominium. So it has a size, a waveform, a location, an orientation, and then we have a whole bunch of receivers laid out. So let's say we've got RX1, RX2, RX3. And then each of those has, we're measuring time series. And then potentially to like force some flexibility, let's say that this one is measuring XY, this one is measuring XY, this is measuring V. Just to like force us to think through this. So, okay, so we have a single source, and now the receiver, maybe 2 sources, whatever. The time series that we want to work with, they're all the same. So we actually only need one projection.
But people could QC it and ditch sometimes, and one receiver and not the other.
That's
So,
fair. That's fair. Okay.
So you're incorporating the orientation like XY into a receiver, right? So you're not thinking about receiver 1 X direction, okay, and then receiver 2 same location, but maybe same XY coordinates, but maybe the Y component or something like that.
Let's remove the
because right now you're kind of simplistically always doing X, Y, and Z, but in real life, it's going to be a combination of 3.
Right. So just, I mean, here's why, kind of like the UBC thought process of, okay, for an EM field, okay, I'm measuring electric, or I'm measuring a voltage, right? So it happens to be this one, and then if I change anything, then that's a different receiver. So even though they might be at approximately the same physical location, it's like a new receiver. So each data has its own receiver.
So then maybe the thing
or they could share it. I mean, you could measure the same receiver multiple sources. So you want to be able to keep that receiver, reuse that receiver.
Yeah, so like in that case, actually, current structure works pretty well because it could have actually location or locations. So like Doug mentioned, like I got a dipole. Basically, you can discretize the dipole to a couple of locations. Receiver know how to integrate that over.
Yeah.
Yes, that's kind of like in general, I kind of like it.
You're just not indexed. You're just saying.
Yes, I think it's that was like a yeah, you're right. But so if you have somewhat like a second level that can kind of do a little bit more efficient way in a survey class level, that might be useful. But, otherwise, then we basically need to do a UVC format basically, right? So you have like a separate like location file, receiver sources, and for unique receiver and sources. Then you basically generate an index map to generate a survey. So yeah, like we could do with that.
This is a good point, and I think that maybe actually what's the issue is actually just our definition of receiver as a unit, not quite right. Because if we loop over sources and it has a receiver list, like that's fine.
That's fine.
The receivers can actually be, you can pass the same receiver to multiple sources, and we're not duplicating information. It's just we haven't actually properly defined what a receiver is as a fundamental unit, like because of this duplication, right? So then maybe actually a receiver, instead of trying, because right now the way that we separate.
Yeah, so right now it's a component, so the receiver, I can just move components out.
Well, is components just a list? So instead of just a single component, you can have a list. So receiver can be listening to real or a match or real and a match.
Okay.
Yeah.
Because right now that's just a scalar, but if we turn it into a list, then that potentially.
Yeah, turn it into a list. Yeah, hold it. Yeah. This is the third dimension that you're talking about.
Yeah.
Yeah. Or both.
Yeah. Well, that's the idea of the list. Is it could be a list of one, or it could be a list of both.
Good question. I was thinking
That's okay. Okay, we're just checking this.
Yeah. So then does this start to
That's you can do like a similar idea, like even impedances. You can dump into everything to one receiver.
yeah.
Like,
Then what do we actually like?
oh right, yeah. You have
Call it receiver?
orientation.
Well, so that gets tricky is because, okay, so now we start to have a question of if we have multiple orientations, then we start to have multiple projection matrices. That's sort of getting messy.
But you have different orientation.
Okay, at least for the EM code, if we actually only have X, Y, and Z, and that's all that we're listening to, and the data that they've given us, they've rotated it into X, Y, Z, then I only want one orientation. Because then, like, the projection matrix is unique to that grid. There's no sense in, like, messing around with having three different.
Actually, I'm curious how the MT code like then like what do you pass for the orientation for your receiver? I think there are no orientation, right? Like it's like they basically like pass that XX, that XY.
Yeah. Yeah. Okay. So it passes X. So like this doesn't have to necessarily be like a required property of the base class.
So I'm thinking about it. Basically, each component is something that we share the same projection matrix.
Yeah.
It goes from a certain grid to a measurement
know, or however many components, it's just associated with one projection matrix, no matter what you think of as a component.
You see, to me, this is a way to approach a problem that is purely numerical. People that just want to do like X, Y, Z experiments in a lab, but in real life, it makes no sense to do this because your fields are never oriented in X, Y, or Z, right? So we'll need all the receivers are always going to be different. They're never going to be lined up. So